Okay, now continue with the earlier problems. Now horizontal shear equation is, some problems will take on this one. Horizontal shear equation is, assume that we have a frame like this, A, B, C, D. You are applying a load P, this length L by 2, some I value. This is some L1, some I, some values of I. Okay. Now maybe there is some load on BC or may not be there on the BC. Now when you are writing the horizontal shear equations or when you are writing the final the end moment or slope deflection equations, we assume that all moments are clockwise. That means positive we assume. Then after solving, any result works out to be negative, then we change the direction for that moment. Then accordingly the end moments we write. Okay. This is first point. In slope deflection method, all unknown final end moments are assumed to be positive. End moments are assumed to be positive, that is clockwise. If any result works out to be negative, then we change the direction for that moment. Okay. Now when you are drawing the free body diagram of all the members, this is your now solution. Okay. Now this is our frame. A, B, C, D is one portal frame subjected to a horizontal load P. Horizontal shear equation means sigma x is equal to 0 equation we have to write. Then this is the point. Slope deflection method, all unknown final end moments are assumed to be positive, because which is positive, which is negative, or which is clockwise, which is anti-clockwise, we don't know beforehand. So assume all end moments as positive. If at all any result works out to be negative, then only we change that direction of that moment. Okay. What it means is, solution, you draw free body diagram of AB. This is AB, let us say. Okay. Then BC, then CD, like this. Okay. This is some note. Okay. So this point, let us say A, B, C, C, D. This point, there is a load here, P. This point, let us say E. This is say E. Now, this is the free body diagram. On that, you have to show the moments. MAB clockwise, you will take it. MBA is also clockwise. Final end moment at B for the span BA clockwise. MBC also you will assume clockwise. But which is wrong? But which is correct? Is this correct or this correct? We don't know. If at all one is correct, another you will get automatically negative sign. That means negative result you will get. Then we will change for that. But first you assume all of them clockwise. This is MBC clockwise. This is moment at C for the span CB. MCB also clockwise. This is the meaning. In slope deflection method, all moments you assume that they are positive. MDC, this length is L1. Now, we take the help of principle of superposition to find the reactions. Sigma x0 means, as we have told you, when P is acting right side, HA will act left side, HD also left side. So sigma x0 horizontal shear equation means P, HA, HD you have to take it. That means with the help of these free body diagrams, you require to find what is HA and HD in terms of the unknowns. Let us see how to find. This length is L by 2, L by 2. Because of P, the two reactions are P by 2 here, P by 2 here. Next, due to the end moments, this is clockwise, this is clockwise. So MAB plus MBA clockwise you are getting. So to balance them, you will get anti-clockwise. Here, anti-clockwise. Clockwise means anti-clockwise couple. This is MAB plus MBA by L. This is the total reaction is HA. Come to this one, MCD clockwise, MDC also clockwise. So anti-clockwise reactions will develop like this. How much? MCD plus MDC by L1. Here also MCD plus MDC by L1. Now horizontal shear equation means this is HA, this is HD. Add them, that's all. Now I'll show that here. Sigma x is equal to 0. Right side positive, left side negative. Deals with only external actions and external reactions only. So now plus P, this is acting at E. Next minus P by 2 because acting left side, this is at A. Plus acting right side, MAB plus MBA by L. This is also plus MCD plus MDC by L1. This must be 0. Now this is your horizontal shear equation. Now in the exam, 4 options will be there. Those options you can simplify, or if you simplify this one of the options will match. P minus P by 2 means plus P by 2. If they put it on the right side, they put minus sign. Left side only are there. Whatever form they ask you, you check which one will tally. So in 2 minutes time, in other words say 1 minute time, horizontal shear equation means from the given diagram, draw these 3 free body diagrams. Then find the reactions here and here. That's why in the moment distribution method also I told you, you must learn how to draw the free body diagrams. Because they will not ask you the complete problem. When they ask you a small part of the problem, the small part of the structure we should be able to draw as a free body diagram. That diagram will let you complete within our stipulated time. Okay, so this is one thing, most general case. Now let us see how they asked in one of the papers in the exam. This is horizontal shear equation. It is not necessary that they should ask you always only horizontal shear equation. Vertical shear equation also you can write. Vertical shear equation happens if the frame here it is swaying horizontally. Supposing that if the frame sinks, then vertical shear equation we have to use. Let us see how that looks like. Now let us see one more question. vertical shear equation is, assume that now you have a frame like this. Length is L, I. You are applying a load P. This point, let us say A, B, C, D. Now, due to this vertical force, it will not sway, it will sink. So, you have to write sigma y 0. So, for that again free body diagram of AB, CD are enough, or AB, BC, CD also if you want you can write it. That is our choice. Okay. Now, if you show that one, draw free body diagram of AB. This is AB. Next BC. Next CD. Like this. Whatever way frame is there, you will show all the quantities. Okay. This is A, B, B, C, C, D. This load P should not be kept on any free body diagram. This P is entirely not taken by AB or entirely is not taken by BC. It will share. P will be shared by these two members. Now, how they will share? Free body diagrams will decide how they share. So, as in the earlier MDM also I told you, any load that is acting at the joint, that should not be kept on any free body diagram. Individual free body diagrams will take care of that. So, you will have to keep P here. I write here, it should not be kept on any free body diagram, because it is shared by two members. Okay, so we leave it at that. Now the moments. Now MAB you have to take clockwise. MBA also clockwise. Here MBC clockwise. MCB also clockwise. Here MCD clockwise. MDC also clockwise. Now sigma y 0 means vertical shear equation. When I am pushing it down, there will develop a vertical reaction VA. There will develop a vertical reaction VD. Sigma y 0 means what you have to deal with. Whether moments developed or not, sigma y 0 means plus VA minus P plus VD must be, sum must be 0. That is sigma y 0. That means here VA, VD you have to calculate and use it in the sigma y 0. So, if you show the free body diagrams here, you see this is clockwise, both clockwise. So, anti-clockwise you have to show, couple. How much is that here? MAB plus MBA by L. This is actually reaction VA. Other points we are not interested. This is also same thing, MAB plus MBA by L. This you don't have to show here. How much you have to show here? Actually, out of P, this fellow has taken so much. Now, net force is how much? This plus this must be equal to P. That means, at this point, how much force will be there? P minus MAB plus MBA by L amount of force downward will be there. Then, if this and this, when you add it, that will be equal to this one. So, that's why we don't show anything here and here, because you don't deal with this one. This free body diagram. Coming to CD and DC, both of them are clockwise, so anti-clockwise. This is MCD plus MDC by L, downward, upward. MCD plus MDC by L. Like that you will get. This free body diagram we are not interested. Now you see VA means this one. P is this one, then VD means this one. So, this plus this sum must be equal to 0. That is sigma y 0. This is the problem. sigma y 0, upward force is positive, downward force is negative. It is called vertical shear equation. Why vertical shear equation? Those reactions will act as a shear force on the beams in the vertical direction. Similar to horizontal shear equation, you have now vertical shear equation. Again deals with external actions and reactions only. Deals with external actions and external reactions only. That's all. Now VA, MAB, what you get is plus VA plus VD minus P is equal to 0. This is the equation. What is VA you get? MAB plus MBA by L plus VD, MCD plus MDC by L minus P is equal to 0. If you push it to the right side, you will get MAB plus MBA plus MCD plus MDC is equal to P into L. One of the options will be this one. This is the vertical shear equation. That means one additional equation we require because it sinks. Okay. Now, here you see VA is acting downward, so we must take it as minus only. Here it is minus. Minus VA going down, minus P plus VD. That means this quantity is minus. Minus. So that means both these two are negative. Minus MAB minus MBA plus MCD plus MDC is equal to P into L. Or we can write MCD plus MDC is equal to MAB plus MBA plus P into L. Our choice, one of the options will be this one. Now, this type of free body diagrams we have drawn in strength of materials many places. That sharing P should not be kept on any free body diagram because it is shared by two members. So, where you have drawn such type of free body diagrams is like in SM also is this way. More familiar example I tell you so that these diagrams will not trouble us. Supposing that you have, this is from strength of materials. Assume that we have a simply supported beam A, B subjected to central point load W, L by 2, center says C. Now we know VA is W by 2, VB is also W by 2. I want to draw free body diagram of AC and CB. Then when you are drawing free body diagram of AC or free body diagram of CB, W should not be kept on any free body diagram because W is shared by two members. This is what you have done. AB, BC. This is AC, CB. Now this W you have to keep somewhere here. It should not be kept on any free body diagram. Same reason, because it is shared by two members. Now there is a reaction here VA. Individual free body diagrams will decide how much will be there that value. VB is also W by 2. This is what we know. Now you see how to keep it in equilibrium. Because this structure is in equilibrium, any small piece of that structure you take it individually or in its isolation, it must be in equilibrium. So AC must be in equilibrium. This length is L by 2. If there is upward force to balance this one here, there must be a downward force W by 2. So sigma by 0 tallied. Now is it in equilibrium? See here, this force and this force together will form a couple. A pair of equal, oppositely directed, non-collinear forces is called a couple. The only effect of that couple is moment given by any force into distance. So what is the clockwise couple? W by 2 into L by 2. So to balance this clockwise couple, there must develop an anti-clockwise moment. W by 2 into L by 2, WL by 4. So this is over. Now come to this free body diagram. W by 2 up. To balance it, here it should be W by 2 down. Now it is anti-clockwise couple. W by 2 into L by 2, WL by 4. To balance that clockwise, it will develop WL by 4. Now if at all you shunt the two free body diagrams, W by 2 down, W by 2 down, put together W, it will tally with this one. Okay, so that means this effect is shared by these two members, so we don't have to show anywhere here. Then where it will be? Nowhere. Now when you join them, total became W. Now you can cut, take, throw. We don't deal with that at all. Okay. So now individually this and this are completely in equilibrium. Then you studied that moment at C, moment at C is WL by 4. Stand here, section right side anti-clockwise, it will sag. So plus WL by 4, this is also plus WL by 4. Then bend moment diagram looks like a triangle. That's what you have studied. Not just here, everywhere in strength of materials, structures, plastic analysis, everywhere, if load is acting at a joint, on a member, if you are drawing the free body diagram of the members separately, that point load wherever you are cutting, at the cut section itself, if point load is there, that should not be kept on any free body diagram. That will be part of that is taken by AC. How much of that part? Individual free body diagrams decide. So this free body diagram tells you that out of W, this fellow will take W by 2. The remaining W by 2, this fellow will take. That's all. Now we can take it out. So same thing we have done here also. Okay. Now let us see one more example on horizontal shear equation. Now next question. Horizontal shear equation is. This in one of the prelims, they have asked this question. Assume that we have applied a load P. This point say A, B, C, D. Length is L, L, this some length L, whatever it is. Okay, horizontal shear equation. Now we have to draw the free body diagrams of all members. Now you see, horizontal shear equation means P when you are pushing it right side, reaction will develop HA, here also HD. So you have sigma x0 means P HA, HD. Sum must be 0. That's what you have to write in 2 minutes time. Now take the free body diagrams AB, BC, CD. 3 we are drawing AB, BC, CD. Okay. Now P is acting at the joint, that means it should not be kept on any free body diagram. Kept on any free body diagram. Next, moments. Here it is 0 because hinge support 0 kilonewton meters. This is MBA clockwise, MBC also clockwise, MCB also clockwise, MCD clockwise, and this is 0. So, like this all moments we assume that they are positive. One MBC will have to be minus MBA only, but whether MBA is positive or negative or MBC positive negative we do not know. But if it is correct direction, this has to be opposite. If this is correct, this has to be opposite. But beforehand, before the analysis, you do not know. So, we assume positive only and we change the direction. Whichever value, when you are back substituting all these slopes, whichever value gives you negative value, that for that you change the direction. Now, you see, P is not acting on this free body diagram. P will be shared by this one. How much of P is taken by this one? This free body diagram will decide. Okay, you do not have to worry will it take P by 2 or P by 3, free body diagrams will decide. Okay, that way. Now we see clockwise, clockwise. So, anti-clockwise reaction like this. This is MBA by L, that is all. Here MBA by L. Now, out of this force, this is taken this much, then here it should be right side only. How much right side force should be? P plus MBA by L. Then P plus MBA by L minus MBA by L. When you are cancelling it, net P will come like this. So, as per this equation, here it will act P plus MBA by L. But that we are not interested. How much they will take? Free body diagrams will decide. This is clockwise. So, to balance it, anti-clockwise couple will form. This is MCD by L, MCD by L. Now, your horizontal shear equation is sigma x is equal to 0. Right side force is positive, left side force is negative. What we have to take all red color? P, HA, HD. Here P means this P we have to show. This is HA, this is HD. So, you will get this is acting right side, so plus P. This also acting right side, so plus MBA by L. This is acting at A. This is MCD by L. This is acting at D, must be 0. So, from this you can write MBA plus MCD is equal to minus P into L. This is 2 marks. One of the options is this one. If they do not ask in this form, BA and CD options, they can ask some other way. Now you see, this free body diagram tells you another way of writing the same thing. MBA, MBC must be equal, oppositely directed. If you assume that this is correct, or wrong also does not matter, but MBC must be opposite to this one. So, I can write MBC is equal to minus MBA. Here MCB I can write minus MCD. They have to be equal. So, MCD I can write it as MBA I can write it as minus MBC. So, this value I can write it as minus MBC, same equal. MCD means I can write, if I put minus here, minus MCB. MCB, MCD, both of them are equal and oppositely directed. Now, we see all minuses if you cancel, you can get now this is MBC plus MCB is equal to P into L. Both are same. MBA plus MCD is minus PL or MBC plus MBCB is equal to plus PL. Both of them are equivalent. So, in the 4 options, they can give you in this form or in this form. First check this one. If this is option, then check this one. Okay, you have only 2 minutes time, lot of time is there. In 1 minute, you can close the issue. Okay, now in another paper, they asked, this is one paper they asked, they didn't trouble you, these options they have given, but they can give you this also. In another paper, in one of the civil services, instead of giving this way, they asked in this form. Okay, let us see how all, if the load is acting on this span. Which one of the following represents equilibrium equation among horizontal forces? Okay, now this is a problem. This is a frame, let us say. A, B, C, D. There is a UDL of, let us say, 10 kilonewtons per meter. Length is 4 meters, 4 meters. This is some length, let us say this also 4 meters. Okay. Now, 4 options were given. MBA plus MCD is equal to 40. MBA plus MCD is equal to 20. MCB plus MBC is equal to 40. MCB plus MBC is equal to minus 80 plus 80. Like this they have given. Now, one of the options you have to take it. Available time, let us say only 1 minute. No calculations, no great thinking is required. Quickly you should be able to draw A, B, B, C, C, D. 3 free body diagrams we will draw. AB, BC and CD. A, B, B, C, C, D. This length is 4 meters, 4 meters. Then we have UDL of 10 kilonewtons per meter. This moment is 0. This is MBA, MBC, MCB, MCD. This is 0. Now, reactions let us see. Due to 10 into 4, 40 kilonewton is acting like this. From left to right 40. How it will share? The reactions will be here 20. Out of 40, 20 this fellow will take, 20 this fellow will take. Next, MBA clockwise, then anti-clockwise, MBA by 4, like this. This is also MBA by 4. So, principle of superposition, due to load what is the reaction, due to moment what is the reaction. Here it is 0, that's why only one term came. Now here clockwise, to balance it, see how my finger should move, anti-clockwise. Here is going right side, left side. I cannot put anti-clockwise like this because it will not form a couple. Two forces if I show this way, no perpendicular distance, so no couple will form. So it has to be like this only. Okay, this is MCD by 4. This is also MCD by 4. Now sigma x 0 means horizontal shear equation. Coming to this one, when I push it to the right side, reaction is left side, HA, HD. So sigma x 0 means UDL, HA, HD you have to add. Now when you add that one, you will get like this, sigma x is equal to 0. Right side force is positive, left side force is negative. Only actions and reactions you have to show. This one, this is the UDL, this is HA, this is HD. So 10 into 4 acting right side. So plus 10 into 4. 20 is acting left side. So minus 20 acting at A. Plus MBA by 4. This is also acting at A. This is also at D, acting right side at D. So at A, D, UDL only you have to write. Must be equal to 0. 40 minus 20 plus 20. 20 into 4, 80 plus 80. Push it to the right side. So you will get MBA plus MCD is equal to 20 into 4 means 80. Minus 80 you will get. This is the equation. See here, MBA plus MCD. 40 is there, 20 is there, minus 80 is not there. Then what to do? At least 80 is telling here, so D you can answer, but options is looking different. That means he is not asking you in terms of BA and CD. Now you see, MBC I can write it as minus MBA as in the earlier problem. MCB means minus MCD. So we can write now like this, MBA plus MCD is equal to minus 80 is what you got it. So MBA I can write it as minus MBC. This I can write it as minus MCD is nothing but minus MCB. All minuses cancel them out. So you will get MBC plus MCB is equal to 80. So correct option is MCB plus MBC is equal to 80. 2 minutes time for this type of calculations. Now this is about the slope deflection method. If slopes are unknowns, or if you have to write a horizontal shear equation, then we will use to find the horizontal reactions. We use the slope deflection method or this type of free body diagrams. Okay, now I remove this part. This is the only scope of the problem. Sometimes write the slope deflection equation or simply slope deflection equation for member BC. Then MFBC plus 2EI by L into 2 theta B plus theta C minus 3 delta by L. That's all. Direct whatever I told you in the fundamental, they don't go most of the times beyond that. But some thinking, maybe 15-20 seconds thinking is required, then this type of problems will come. Okay. So now many other questions as you see in the gate and prelims, they are just direct substitution, no need to think at all. Even this much thinking is also not there. So when you see those questions, directly by inspection itself you can answer, or you will spend 10-15 seconds time. So this is about the slope deflection method. Now we will study about a special structure called cable, how they behave. Analysis of, this is your ninth topic. Analysis of cables. Now the characteristic of any cable, is EI by L. Flexural stiffness is approximately equal to 0. Not flexural rigidity. Flexural rigidity by L is approximately, or this called flexural stiffness. Cable means length is very long. Sometimes it runs into 100 meters, 150 meters, like that. So length is so long that EI by L quantity is approximately equal to 0. So that is the characteristic of a cable. Because length being very long, you cannot apply compression with respect to the cross sectional dimensions. Length is very large. Supposing that you take a small thread, cross section is very thin. So even if you take 1 centimeter length of the thread also, you cannot apply compression because it gets slack. So on the cable, you cannot apply compression. It says I cannot take it. Neither you can apply bending moment. Before you apply bending moment, it simply rotates. So cable is a structure where it cannot take compression, it cannot take bending moment, but it can take tension. If you pull the cable, it will take it. Till it breaks, you can pull it. So cables can only take tension. If they use the word cable, the implied meaning is automatically that only it will take tension, no compression, no bending moment. If length is very less, then cable can become like a rod, or can become like a link, or it can become like a bar. Rod or bar or link all mean the same. If you use that word, then they can take a compression and tension but not bending moment. Bending moment, if at all it takes, then we call it as a beam, not rod, not bar, not link. Okay. So accordingly, we see the once you see the word of the what word they are using, you must manage the questions accordingly. First point is concepts. Cables cannot take compression and bending moment. They can only take tension. That means bending moment is 0 everywhere in the cable. Then accordingly, this is how the nomenclature. If you use the word cable, can only take tension, no compression, no bending moment. If the cable length is very less, then it behaves like a rod. Rod, bar, link. These all mean the same. They can take tension and compression, but not bending moment. If at all there is a bending moment, we will not call it as a rod, we will call it as a beam. Okay, can take tension and compression only. Tension and compression only. Bending moment is 0. In the why it is necessary for us to understand this one is that will help us in drawing the free body diagrams fast. If they give you a structure, once they put a rod, let us say, they say the word rod, then you are sure that in that rod there is no bending moment. So when you are drawing free body diagram, only you will show axial force. So to draw that free body diagram accurately, that wordings will help. The understanding of those words will help us. Okay, bending moment is 0. Then beam. Beam means primarily subjected to bending moment. That means only bending moment. Some amount of compression if you can neglect, then it is called beam. If you cannot neglect any compression, then it is called beam column. That means compression is there and also bending moment is there, like that. So accordingly, beam column, when we use the word like this, first word is beam, next word is column. That means primarily there is a compression, bending moment, then there will exist compression also, which cannot be neglected. Here compression you can neglect, then we call it as a beam. If you cannot neglect, it becomes beam column. So primarily subjected to bending moment, subjected to bending moment, but there will be compression also. But there will be compression also, which cannot be neglected. Here compression can be neglected. Compression force is less, can be neglected. If it can be neglected, beam. If it cannot be neglected, beam column. Then what is a column? Only column they use say. Primarily compression, but there will can develop bending moment also as a secondary force. Primarily subjected to compression, but there will be bending moment also. If bending moment is not there, then that we call it as a strut. Only compression means strut. It is like a truss member. Okay. So it's that like this. Cable very long, so flexible. Cannot take bending moment, cannot take compression, only tension. If it can take tension and compression both, then we call it as a rod or bar or link. If it takes only bending moment where you can neglect compression, it is called beam. If you cannot neglect compression, then it is called beam column. Primarily bending moment will be there. Column means mainly compression, but there can be moment also. Such members we call them as columns. So in these things, this differentiation will tell us that how to draw free body diagrams in the exam. One of the questions we will discuss. If we know that what is the meaning of that word, then drawing the free body diagram becomes difficult. Okay. Now, in the cables chapter, there are only two concepts. If you understand those two concepts, then any problem given in the cable structure problem, you can complete in 30 seconds time. They don't ask you any question which takes more than 30 seconds time. If they give us, not you, nobody will solve. Like one of the papers, they have asked it as a 20 marks question. Calculators are required to answer that question. But if you attempt such questions, you may, first thing is, lot of time is wasted. That is one loss. Second loss is so many other questions we will lose more marks by attempting such questions. Okay, you must learn to fight where the opposition was very strong. Let us say you should come back, you should resign from that question and attack other problems. Finally, what that matters is how many more questions are you solved it correctly. That's all, not a particular question whether you solved it or not. So, where calculator is required, where question looks very tough, come back, attack other problems. Finally, many answers you will solve. If you sit down only on that question where calculator is required, 2325 is equal to 4567, multiply it, then after that cube root it, then cube root. 6th class you have studied about how to find the square root of a number, then draw one table. All that if you have to do means time is gone. Okay, you may get that solution, but finally we end up losing too many marks. So, in the exam, in this fashion, whatever way I am explaining, if the questions come in that fashion, generally 95% of the questions are like that only. One question at the most. Structures especially, you will not even miss a single question. If at all you have miss, not only you, everybody will have to lose that 1 mark or 2 marks question. Okay. Now, as I am giving you the overall view of the structural analysis, you should now understand that questions will be only that simple. If they don't give you like that, not you, nobody will answer in the exam. Okay, this is your first concept, what a cable is, what forces it can be subjected to. Then during the process of analyzing them, which concepts will help us, that you write it as a second point. This is what in engineering mechanics we have studied. Assume that we have a bar or any other structure subjected to two forces. This is P, this is a Q. Now, for these two forces to be in equilibrium, three conditions have to be satisfied. Q must be opposite to P, and Q value must be equal to P, and Q must be along the same line. That means it must be collinear. Collinear means same line of action. So, to keep two forces in equilibrium, they must be equal, oppositely directed, and collinear in action. This point is very much required. Though it is known to us, but can we apply in 10 seconds time or not is the point in the exam. Conclusion. To keep two forces in equilibrium, they must be equal, oppositely directed, and collinear in action. These are the conditions: equal, oppositely directed, and collinear. Then third point, how to keep three forces in equilibrium. Assume that we have a block like this, subjected to only three forces. This is P, let us say Q, this is say T, this point say O. Only three forces are acting, and assume that it is already in equilibrium. That means equilibrium already happened. Now sigma x0, sigma y0 happened. Sigma m also must be 0, otherwise it will rotate. Let us see sigma m is equal to 0 happens or not. Sigma m is equal to 0 should happen about any point you take, whether inside the structure or outside the structure. Sum must be 0 only. Moments of all force about any point must be 0. If it is not 0 about any one point, about that point the body rotates. It won't be in equilibrium. That's what you have studied. Now let us see, take moments of these three forces about point O. P is passing through O, Q is passing through O, so they give 0 moment, but T is not passing through O. That means T will give some moment about O, T into some perpendicular distance. Because of that it will rotate anti-clockwise. To balance that clockwise moment is not there. These two fellows say I cannot give any moment about O. So it means that T cannot act like this if it wants to be in equilibrium. The T has no choice. It has to be in this direction only, like this. It must pass through O only. Then T also will give 0 moment. That means to keep three forces in equilibrium, they must be concurrent. Concurrent means meet at one point. Assume that the three forces are concurrent and T force is acting say out of plane like this way, either perpendicular or some other inclined direction, but not in the plane of the board. And PQ are forming a plane. Let us say it is the plane of the board. T is out of plane, let us say. Then what will happen out of plane? If I take out of plane sigma z is equal to 0, P cannot have a component in this direction because 90-degree angle. Q also cannot have a component in this direction. Same problem, 90 degrees angle. But T cos theta or T itself, that is not balanced because backside nobody is there. Only three forces are there. So because of this T force, this body will translate. It will not be in equilibrium. Because nobody is there on the backside of this body. That means T has no choice. It cannot be out of plane. Nobody will balance that force. It has to be in the same plane. That means to keep three forces in equilibrium, they must be coplanar. Coplanar means lying in the same plane. So, if they don't lie in the same plane, rigid body translation. If they are not concurrent, rigid body rotation will take place. So, conclusion. To keep three forces in equilibrium, they must be coplanar and concurrent. If they are not coplanar, rigid body translation takes place. If they are not concurrent, the body will rotate. Rotate as a rigid body, like that. Now, after studying this one, supposing that you get a doubt, say, in strength of materials, you have studied a beam subjected to central load. The two reactions are like this. Now, on the body, three forces are acting: W, W by 2, W by 2. But these three forces are not concurrent, means they are not meeting at one point, but still it is in equilibrium. So, but this thing does not come under three forces in equilibrium, two forces in equilibrium only, because this W by 2, this W by 2, I can replace it as a resultant like this W. That W is at the center only. Now you see, this problem is a case of two forces equal, oppositely directed and collinear. You should not treat this as three forces, and because that W force you have split into two parts and kept it at different distances, but whose resultant is this only. So it is a case of two forces which are equal, oppositely directed and collinear, so it is in equilibrium. It is a case of two forces which are equal, oppositely directed and collinear in action. Now let us see how the numericals come in the exam. Only these two concepts are enough: how to keep two forces in equilibrium and how to keep three forces in equilibrium. They must be coplanar or concurrent. If these two ideas, if you have, whenever you are solving the cables problems, keep in mind that that question involves concepts of these two only. Then your way of thinking about the problem completely changes and you can solve it in your stipulated 30 or 40 seconds time. A rigid uniform straight bar BC of length 2 meters and weight 2 kilonewton is kept in horizontal position. Is kept in horizontal position by two cables as shown in figure. Sag at E is. Now we want to find what is the sag. This is the cable profile. This point is say A. This point, there is a load here we are hanging, a load of 1 kilonewton. This point let us say B. This is actually a cable, but when you are pulling it, it takes up a straight path. A, B, C, D. This point let us say E, B, C, D. This level difference between A to D is 1 meter. Now this is in the horizontal position. This is the rigid uniform straight bar. From here to here, this distance is 2 meters. This is also 2 meters. This is also 2 meters. This is the problem they have given. In one of the engineering services, it was a 12 marks question, but in where you have to explain say 2 minutes time. But if it is asked in a gate type examination, which is a 2 marks question, you must finish off in 30 seconds time. What is the sag at E? Okay. So let us see how we should think of the problem. If you take the free body diagram of the BC, its weight is 2 kilonewton. That will act at its midpoint. This is the weight W. Its value is 2 kilonewton. So on this will act at the CG. That means this is 1 meter. This is also 1 meter. E, A, B, C, D, E. This point let us say F. Let us call this point is F, where that CG is there. This point is CG. Okay. Now, if at all, free body diagrams are drawn generally like this. If at all I cut the cable here at between C and D somewhere, if I cut it, then what this piece of the cable will do? That means when you are drawing the free body diagram of BC, on BC, what this cable CD is doing, you have to show. For that, what we do is we will cut the cable, then it will fall down. But now it is not falling down, means what this portion of the cable will do on this one? Will that piece pull the cable or push? Once it is falling down, means this must hold him and pull him like this. So when you are drawing this free body diagram of BC, what cable is doing, you have to show. So this cable will exert a tensile force T. Let us say its angle is T1. This angle of inclination, let us say theta. Okay. Now similarly cut this cable here. Again it will fall down. Now it is not falling down, means this piece of the cable on this one, we should exert an angle of alpha. When you cut it, this is T2, let us say. So T1 theta, T2 alpha. Like that. Now, if I take BC free body diagram, on BC, three forces are acting. Weight of the member, tensions of the cables acting on BC to keep him in horizontal position. Now, as I have explained to you, if three forces are acting on a body, to keep that body in equilibrium, those three forces have no choice. They must meet at one point. That means they must be concurrent. So, if I extend this line, this weight line it cuts somewhere here. Then this line, when I extend it, it must pass through this point only. Otherwise, beam will not be in equilibrium. This is F is already over. Now this point you take it as a G. Now you see, if this angle is theta, it has to be theta because alternate angles. It is like similar triangles. BF, FC same, height is same. So in this triangle and in this triangle, if this is theta, this has no choice. It has to be theta. That means this alpha is alpha here. Alpha has no choice. It has to be theta. Otherwise, they can't meet at G. Okay. So now, if I extend this line, it will cut here G. This point say H will take it. What's the length here? 2 plus 1, 3 meters. So now GHD will form one triangle. Now same way I will extend it here. Okay. This GHI you take it, GIE. If this is theta, it has to be theta. Then this also has to be theta. This length is also 3 meters. Now again another set of similar triangles formed. GHD is one triangle, 3 meters theta. GIE is another triangle, 3 meters theta. Which means that EI, DH must be same. Which also now means that E and D are at the same level. Now question is this one. What is the sag at E? Now they have to be in the same level. Otherwise this will not match. So sag at E has to be 1 meter. If it is a 2 marks question, just draw this diagram and just answer it as 1. You don't have to explain to anyone why that 1 meter came. But if it is a 10 marks or 12 marks question, you must explain this one. What is the need for the 3 forces to meet at one point? Otherwise, they will not be in equilibrium. So that condition you have to write. That is the only difference. Now you see, this is your solution. If it is 12 marks means that one line you have to write. From the free body diagram of the member BC, first point, this is what you have to write if it is a 12 marks. From the free body diagram of member BC, to keep 3 forces in equilibrium, what are those 3 forces? T1, T2, W. Equilibrium, they must be concurrent. They must be concurrent. That is, they must meet at point G. Next, second point. From similar triangles concept, that is triangle GHD and triangle GIE, theta must be equal. Theta must be equal. It means that D and E are at same level. So sag at E is equal to HE is equal to 1 meter. If it is a 12 marks question, you have to explain this one. 2 marks question, even that is not required. Simply take 1 meter, enough. Supposing that if they ask you, what is the tension in the cable AE? or they can also ask you what are the support reactions. This I remove now. Sag at E is 1 meter. Now let us see the next part of the problem. This problem involves how to keep two forces in equilibrium. Okay. Next question. In the above problem, tension in the cable AE is now let us see how to find the tension in the cable AE. The tension in the cable means first you have to find the reactions. This is, let us say, VA, let us say HA. Okay, then here you will get VD, HD will be outside because when you are pulling it, the supports will exert reactions outward. Otherwise, they will come in and it will fall down. Okay, so we have to find the reactions first. Assume that VA and HA you have found. Then I can replace the resultant of VA and HA by a single force. That resultant of VA and HA has no choice because this is axial force only. Tension can take, AE can only take tension. Now I will cut the cable here. Then this portion of the cable must exert the hinge pull like this. Otherwise, it cannot push it because then it will go up. If pushing is not possible, that means this also must push him. Pushing is not there. So AE. So tension the cable AE. One force is here. There are two forces here. I can replace these two forces by a single force. Then that single force has no choice. It has to be in the same direction like this. This, let us say, your RA. So resultant of VA and HA is RA. Now there are only two forces, RA and TAE. Those two forces to be in equilibrium, they must be equal, oppositely directed and collinear. Otherwise, they won't be in equilibrium. So at this point, you take the concept of how to keep two forces in equilibrium. Here you will take the concept of how to keep three forces in equilibrium. Any question given, either this configuration or this type of configuration only will be there. Okay. So first we will find the support reactions. Now take moments of all forces about D. Sigma md is equal to 0. Clockwise positive, anti-clockwise negative. When you write sigma md is equal to 0, it is equilibrium equation. Equilibrium equation means what? It deals with equilibrium equation but not bending moment equation. What is the difference? Equilibrium equation means what? It deals with external rotational effects of forces or external effects of the movements, whether the body will rotate or not only. If the body rotates, with what acceleration it rotates, we can find. So that is the meaning of that. If it is not in equilibrium, it will rotate. Then with what acceleration? Like that. Deals with external rotational effects of forces. are external effects of moments. External effects of moments. Then what's bending moment equation? It deals with internal effect of the moment. It deals with internal effect of moments. That means whether it is sagging or hogging, it will deal, but not that. Sagging or hogging, we will not worry. Whether it is rotating or not, with sigma m, you will know. But when you take bending moment equation, you will know whether it is sagging or hogging, because you will see only one side of the section. Both sides of the section you take, it's a wherever you take in a structure, sigma m must be 0. Otherwise, about that point, the structure will rotate. Okay, that is the difference between sigma m is 0 and bending moment is equal to 0. So, when you take sigma m 0 plus VA into 8 at A, then minus 1 kilonewton is acting at a distance of 6 meters, 1 into 6, minus weight 2 kilonewton, 2 kilonewton into 3 must be 0. This 1 kilonewton acting at E, 2 kilonewton acting at F should be 0. So, you will get HA also will come, minus HA into 1 must be 0. So, you will get 8 VA minus HA is equal to 12. Call it as 1. Then bending moment at E is equal to 0. Why? Because it is a cable. In a cable, bending moment is 0 everywhere. Not just E. Any point you take it, it will be 0 only. But we know about E only, that sag, 1 meter. If that sag we don't know, let us say, we could not find, say, then you cannot find the reactions also. Okay. So, in a cable, bending moment is 0 everywhere. That's why. So, bending moment at E, if you want to find, what you have to do? We have to stand there, look one side, either left side or right side, our choice. Whatever side you see, you will get the same result. Stand at E, look left. How many forces are there? VA, HA. VA into 2, HA into 1. It must be 0. So, stand at E and look left. You will see plus VA into 2 minus HA into 1 is equal to 0. So, from this you will get HA is equal to 2VA. Call it as 2. Now, 2 in 1. 8 VA minus HA means 2 VA is equal to 12. So, VA you will get 2 kilonewton. If VA is 2 kilonewton, HA is 2 VA. That means 2 into 2, 4 kilonewton. Then HD will be same. HD you will get HA is equal to 4 kilonewton. This you will get from sigma x is equal to 0. Then similarly, VD you will get 1 kilonewton. How will get from sigma y is equal to 0. Like that. So, now here you are getting VA is 2 kilonewton, HA is 4 kilonewton. Now, RA. RA we know how to find, square root of VA square plus HA square. So, TAE is nothing but RA. Then how much is this value? Square root of 2 square plus 4 square. So, root 20. kilonewton, root 20 kilonewton. That's all. So tension in the cable AE is equal to RA is equal to square root of VA square plus HA square root of 2 square plus 4 square. So you will get root 20 kilonewton. Okay. So this is the concept we write. What we have learnt is this I remove. Why they are equal? Tension and RA equal is because of this reason. You can write as a note. To keep two forces in equilibrium, what are they? TAE and RA. They must be equal oppositely directed and collinear in action. This concept we used and said that tension is equal to RA. Okay, now we'll see the second problem. A uniform beam weighing 1800 Newton is supported at E and F. And by a cable ABCD as shown. Determine tensile force. Determine tensile force in segment AB. In segment AB of the cable. Now this is the problem. This is one uniform beam weighing 1800 Newton. Okay. Now this length here is 1 meter. Here it is there 1 meter like this. 0.5 meter here like this it went. Another 0.5 meters like this. Okay. This is a cable. Like this they have tied, and here 0.5 meters height somewhere here. It goes like this, and this is support. Okay, this point let us say A, B, C, D. This is say E, F. Now the distances are like this. This is 0.5 meters. This is also 0.5 meters. From here to here it is 2 meters. Here to here 1 meter. This is 0.5 meters. This sag here also he has given 1 meter. At least one sag they have to give us. Now, this is the problem. It's a 2 marks question. It's a 2 marks question. You have a 2 minutes time. There is one beam here supported by two cables at E and F. CE, BE are two independent cables and they are hanging on to the cable ABCD. So the cable took this much shape. Okay. Now he is asking what is the tension in the cable AB. If you want to find, as in the earlier problem, if you want to find tension in the cable AB, you must know the reaction. If I know resultant reaction at A, then whatever RA is there, AB also same. That idea first we should get. Tension in the cable, which is that cable attached to the support, means support reaction. If I know support reaction, tension in the cable must be equal. So in 2 minutes time, your task is to find reaction at A, and that is nothing but tension in the AB. Now let us see how we should manage. See here, what is the total length of the beam? 1 plus 2, 3 plus 0.5, 3.5 meters. That means center will be somewhere here. This is the weight of the beam, 1800 Newton. Now 3.5 meters means from here to here it is 1.75 meters and this is also 1.75 meters. Okay. Now 0.5 meter here, 0.5 meters here. That means A to D total length is how much here to here? 1.75 plus 0.5. You will get 2.25 meters. And this is also 2.25 meters. So total length is 4.5 meters. And whether this structure is symmetrical or not, if loading is symmetrical, supports will share the load equally. Now you see 1800 Newton, some structure was there at 4.5 meters distance, exactly midpoint. You are pulling it with a force of 1800 Newton. That means here upward reaction we can find from that. VD, vertical reaction is 900 Newton, half here, half here. VA is also 900 Newton. So by inspection we can find that. Next, here 1 meter sag, C point is at a sag of 1 meter, horizontal distance is also 1 meter. That means this angle of inclination is 45 degrees. So if you take the tension in the cable TCD, let us say, tension in the cable and the resultant reaction at D must be in the same as in the earlier problem. This is RD. They must be in the same line. If this is 45 degrees, this has to be 45 degrees. Then if angle is known, VD is known, RD I can find. What is RD? RD cos 45 must be equal to VD is equal to 900 Newton. Now RD is 900 by cos 45, that means 900 root 2 Newton. So now the resultant reaction, now you will get here 900 root 2 Newton. If RD is known, I can find HD 900. The x component of that must be this only, 900 Newton. So 900, 900, resultant reaction is 900 root 2. Now from sigma x is equal to 0, if HD is 900, what is HA? 900. If HA is known to us, what is the resultant reaction in the 45 degrees line? RA 900 root 2. If RA is 900 root 2, if you cut this part out and this fellow will exert a force of this much, tension in the cable AB is 900 root 2. Otherwise the joint will not be in equilibrium. So 2 minutes time, your task is only this much. So tension in the cable AB is 900 root 2, that means 1272.9 Newton. Next, this is we are taking the help of only how to keep two forces in equilibrium here and here, and we managed the solution like that. Either only two concepts, how to keep two forces in equilibrium or how to keep three forces in equilibrium. If you have that idea, then any problem given, you think of say 1 minute time like that and finish off quickly. Now, next point. In one of the GATE papers, it is a 2 marks question. Next one. A cable suspends across a gap of 250 meters and carries a UDL of 10 kilonewtons per meter horizontally. Calculate maximum tension in the cable. If sag is, or if maximum sag is L by 25. So, based on the description, first we have to draw the diagram. This is a cable structure. Complete diagram I am showing. This is a cable, main cable. This passes over the pulley here and goes on the other side. This we call it as anchor cable. Like this it will come. This cable we call it as anchor cable. That is also same. This point let us say A, B. Its span from here to here is L is equal to 250 meters. Maximum sag is L by 25, that means 10 meters. This is called H, dip or sag of cable. You will get 250 by 25, 10 meters you will get. This is what is given. It is subjected to a horizontal UDL. How to apply horizontal UDL on this is, we hang the hanger bars like this, and through that bar it is subjected to UDL like this. So something like that will be there. This is a horizontal UDL of 10 kilonewtons per meter. This value is 10 kilonewtons per meter. Then where this load comes is from the girders. Actually this is one cable, another cable, similar cable will be at a distance of 10 meters. Between them there is a row, that means bridge type structure will be there, and vehicles move forward and backward. Okay. So from that road bridge, the loads will be transferred to the cable with the help of hanger bars. That load he has given 10 kilonewtons per meter. From where this load came, right now we will not worry. After this I will tell you that there must be a beam here, and when the vehicles are moving, the load exerted by the girder on the hangers is 10 kilonewtons per meter, like that. These are called hanger bars. As per IS 800-2007, maximum slenderness ratio should never exceed 160 for the hanger bars subjected to tension. Okay, this is IS 800-2007. Still again we'll discuss those points. Now he is asking you to find what is the maximum tension in the cable. We are not interested in the anchor cable part of the structure. We'll cut here, remove it, cut here, remove it. Only AB part of the structure we are interested to deal with. On AB, this is VA. VA and VB are the vertical reactions exerted by the pulley on the cable. It pulls like that. Then horizontal reaction will act like this. HA and HB are the reactions exerted by the support on the main cable. That's all. Then on the support, anchor cable also will exert some force, that we are not interested. These VB, HB, VA, HA are exclusively due to this main cable. This is main cable, anchor cable. On the support, many other things also may be coming, anchor cable or some other things. They will exert additional reactions on the support. That reactions we are not interested. Only that AB part we want to discuss. Okay. Because of this is 10 kilonewton, 250 meters. Because of symmetry of loading, VA and VB must be equal. See here, support reactions we want to find. VA is equal to VB is equal to WL by 2. W is 10 kilonewtons per meter. Length is 250 meters by 2. 2500 means 1250 kilonewton. Why equal? Equal because of symmetry. Next, to find horizontal thrust, take bending moment at C is equal to 0. Bending moment at C is equal to 0 because it is a cable and bending moment is 0, 0 everywhere in the cable. So why we have to take C? Any other point we can take it, but at C why we are taking is that sag we know at that point only. So bending moment at C is equal to 0. How to find that? Stand at C and look left. When you stand at C, look left, how many forces are there? Here when you stand here, look, see, there is one part of UDL, VA and HA. This anchor we are not interested. This is the portion which is exerting force on the support only. That will not be transferred to the cable again. Okay. So at this point, this is the length is 125 meters. This load from here to here, it is only 125 meters up to C. Then this will act at 62.5. This load from here to here, it is 125 by 2 meters. So 3 forces we have to take. So plus VA into 125 minus HA into 10, HA because it is giving anti-clockwise, load also giving anti-clockwise, minus 10 into 125 is the total load acting from C to A into its perpendicular distance 125 by 2 must be equal to 0. Okay. So VA already we know 1250 kilonewton. So from this HA you will get this HA is 7812.5, 9812.5. Okay. Now, once HA is known to us, VA is known to us, now we can find the reaction. VB is also same. VB is same, 1250 kilonewton. HB is also same, 9812.5. Now, maximum reaction. It's like earlier problem. HB we know, 98 to 12.5, 1250. Now the resultant reaction is RB. If you cut this cable, this is the maximum tension you can get. Maximum tension is developed at highest point in the cable. Minimum tension is developed at lowest point in the cable. So if I take that point, that free body diagram, this is from free body diagram at B. It will tell you that RB is equal to T max. In other words, T max, maximum tension, is equal to square root of VB square plus HB square or VA square plus HA square, anything we can write. So 1250 square plus 9812.5 square. So you will get 9911 kilonewton. So this is the maximum tension in the cable. Again here also, you see how to keep two forces in equilibrium only. What we have done here is the cable, this cable is going like this. That cable free body diagram only we are taking. Cut this anchor cable, throw it out. Support also, support is exerting on the cable this much resultant reaction. That means this cable is held and pulled with a force of RB. In other words, this cable is under a tension of T max. If I cut here, this will be balanced by this one. If I cut here, say, then what the cable is doing on the pulley you have to show. Okay, so cable is pulling the pulley with a force of T max. So it is giving a, in return, the hinge is giving this much reaction, RB. So they have to be equal and oppositely directed. This arrow mark is the force exerted by this cable on this cable. We are drawing the free body diagram of B. When you are drawing the free body diagram of B, excluding the anchor cable, VB, HB and T max, only this we have taken because our interest is only in the main cable. If you are interested in the support, then on this support, VB plus this also will give some vertical force. So that reaction also you have to add. Total reaction at the support if you want, then this also what anchor cable is doing also you have to add. Okay, now assume that the anchor was not there, cable is stopped here only. This for full clarity sake I have given all. So assume that anchor itself is not there, only this is our part of the structure. Okay, if anchor cable is also given, its slope is also given, then total reaction will be different. So 9911 kilonewton. Second, this is the first point we can take, support reaction, maximum tension. Second point is minimum tension is developed at C, maximum tension is developed at B. Because at this point only horizontal component will be there, no vertical component. As you are moving towards the highest point, this load is also must be taken by the cable only. So cable only has to resist. So in the process, maximum will happen here, minimum will happen at C. Write that point. Maximum tension is developed at highest point in the cable, and minimum tension is developed at at lowest point in the cable. Now supposing that if you want to find what is the minimum tension. Now let us see the next question. Third point is, in the above problem, minimum tension in the cable is, you see, you will draw free body diagram of CB. This point is B. I have shown here VB, HB, and this is your T max. We can say R also equal to RA, RB, T max is equal to RB. This value is 9911 kilonewton. Now this I am removing. Why? On the cable directly what the hinge support is doing, we are showing. Then this point, let us say C. If you show this free body diagram, this is the loading. This value is 10 kilonewtons per meter. This total length is 125 meters. What I am drawing is free body diagram of cable CB. Because entire structure is in equilibrium, CB cable alone must be in equilibrium. On CB cable, what hinge will do is this much force. On cable, what UDL is doing is it is exerting downward force. Now, when you cut the cable here, the other half of the cable will exert a tension like this, which we call it as minimum tension. Why it is minimum is, you see, at this point, always tension will be along the axis of the member. So, this is T minimum or T, let us say. No vertical component here because lowest point, if you drop a tangent, it's horizontal. So, tension is also horizontal. Whereas here if we take it, the tension has two components, x component, y component. This x component is 9812.5, y component is 1250. This is what we have written. Now you see 125 into 10, 1250 down, 1250 up. So they have, in y direction they are in equilibrium. Horizontal 9812.5. To balance that here, T minimum has to be 9812.5 only. So minimum, maximum. So if I take sigma x is equal to 0, any force acting right side positive, any force acting left side negative, you will get minus T minimum plus HB is equal to 0. So T minimum, you will get HB is equal to 9812.5. That means minimum tension is equal to horizontal reaction at the supports. Now wherever you take, say, the x component of the tension in the cable, everywhere it is same. Once they asked that point, the x component of tension in the cable is always constant and equal to HB. Okay, wherever you cut here, say cable you are cutting here, then tension will be like this, whose x component must balance this one. y component must balance by this load, whatever load you are taking. So why here maximum is there? X component is this 1250 kilonewton downward is balanced by the upward component to keep in equilibrium. That's why here tension is maximum. At lowest point, no y component. So naturally only horizontal component. So minimum tension will develop. It is always constant at any point in the cable and equal to Hb. This is your third point. Now let us say fourth point. When you studied in second year surveying, chain surveying you have studied. In chain surveying, you take the chain, two ranging rods you take it and you measure the length. If it is hanging, let us say, then due to self weight itself it will sag. Straight length, curved length naturally different. So you have some error due to sag. It is always cumulative error. If 10 times you are using the cable, say chain, so 10 times that error is continuously adding. It is not a compensating error, cumulative error. That's what you have learnt. There you have studied that if a cable or any chain sags due to its own self weight, it takes the shape of a catenary. You approximate that catenary as a parabolic shape and manage the problem, but correct shape is catenary. Okay. So if it is subjected to UDL along its curved length, it takes the shape of catenary. Horizontal load, if it is subjected to, then it exactly takes the shape of parabola. Okay. So now we will write that point. If any cable sags due to its self weight along its curved length, it takes the shape of a catenary. In mathematics, you have studied catenary means it is a cos hyperbolic function. A cos hyperbolic function, cos h function. If a cable is subjected to, if any cable is subjected to horizontal UDL, like as in this case, horizontal UDL, it takes the shape of a parabola. In the exam, you have to be careful. If they give you horizontal UDL, parabola you have to answer. If you take sags due to its self weight, it takes the shape of catenary. Due to its self weight along the curved length means it is catenary, otherwise it takes the shape of parabola. Then self weight due to self weight is also like UDL, but what difference will be there is, if you take the curved length here from here to here, this is the length of the cable. Another length dx you take it, this length is slightly more. If you take another horizontal distance dx say, but this curved length is slightly more, so UDL will be more. Here minimum load, slightly more, here maximum. You see here for a same projected length of say dx, this much length will act, this much length of cable will act on this much length only vertically, whereas here almost same straight line, same load, but inclined line projection length means dx length when you take it, projected length, then load will be more, maximum less minimum. You approximate that because the inclined length here, horizontal length here, difference is very less. But if you take the small difference also into consideration, it takes the shape of catenary. If you forget about that difference, here horizontal UDL self-weight is same, you take it say, then it will take the shape of parabola. So that is the case here. In the exam, you have to be careful. Is he asking shape of the curve due to its self-weight or shape of the curve due to horizontal load? Accordingly, catenary or parabola you have to answer. Okay. Next, fifth point is now fifth point is funicular polygon, or we can also call it as string polygon. Funicular polygon or string polygon means a well supported cable when subjected to loads, whatever shape it takes, that is called funicular polygon. Here in this case, in this particular example, this cable is subjected to UDL. Then what shape it takes? Parabola. That parabolic shape is called funicular polygon. So, funicular polygon. It is the shape taken by a supported cable or string when subjected to loads. When subjected to loads. Then when subjected to loads, which shape it will take? It will take the shape of an imaginary simply supported beam subjected to UDL. Whatever bending moment diagram you get it, it will take the shape of the bending moment diagram of a simply supported beam of same length. Okay. It takes the shape of BMD for an imaginary simply supported beam. For an imaginary SS beam means simply supported beam. Imaginary simply supported beam subjected to same loads. Same loads. Now you see, if you see the strength of materials you have studied, if you have an simply supported beam subjected to UDL, it will take the shape of bending moment diagram is a, this is the parabola. Okay. Now, if a cable is subjected to UDL, this shape of this one is also parabola. This is a parabola. We call it as funicular polygon. The shape taken by the cable is called funicular polygon. In this case, the shape taken by the cable is parabola because that is a bending moment diagram for an imaginary simply supported beam subjected to same loads. Parabola, you will get it, same parabolic shape but in the reverse direction, of course. That's all. Okay. Such examples when I take here, assume that we have a simply supported beam subjected to central point load W. Now, the bending moment diagram is like this. Now, if you take an image cable, now assume that you have a cable of same length subjected to point load, then that cable will take this shape. If you take a cable which both ends are hinged, subjected to central load, hold it and pull it, say, cable will take this shape. This shape is equivalent to the shape of BMD of an imaginary simply supported beam. Okay. Now, this shape, this is cable. That shape taken, we call it as funicular polygon. Okay. Now, assume that we have a simply supported beam subjected to two loads. Second example, some loads W1, W2. Now, the bending moment diagram goes like this, say, this is the bending moment diagram, approximately we have drawn. If you take a cable and if it is simply properly supported cable, this is the cable, dotted line means cable I am showing. When loaded at the same positions, it will take this position. Like this. This load here W1, this load here is W2. This shape taken by the cable, we call it as funicular polygon. Now, you see, this diagram tells you that wherever you are getting maximum bending moment, this is the maximum bending moment in a simply supported beam. At the same location in the cable, you will get maximum sag. Maximum sag in a cable occurs where bending moment is maximum in an imaginary simply supported beam subjected to same loads. Okay. So, this is first as told by Professor Eddy. So, it is named after him, Professor Eddy's theorem we call it. Now, we can say from this one conclusion, maximum sag in a cable, maximum sag in a cable occurs where bending moment is maximum in an imaginary simply supported beam. In an imaginary simply supported beam subjected to same loads. Subjected to same loads. Okay. Now, let us see how to find where maximum sag occurs in a cable. That is a 2 marks question. That means we have to draw an imaginary beam subjected to same loads, draw the bend moment diagram. Wherever bend moment is maximum, at that same location in the cable, sag is also maximum. Let us see one question. A cable of length 100 meters is subjected to 3-point loads. Loads of 100 kilonewton, 200 kilonewton and 400 kilonewton at 25 meters, 50 meters, 75 meters respectively from left support. Maximum sag occurs under point load of like this, point load of 100 kilonewton, 200 kilonewton, 400. Maximum sag occurs under which load, 100 or 200 or 400? It looks as if under 400 maximum sag will happen because load is maximum. But if you draw the diagram, this is a simply supported beam, let us say, an imaginary simply supported beam. Loads are applied like this, 100, this is 200, this is 400 kilonewton. This point let us say A, B, C, D, E. Length is here 25 meters, 25, 25, 25. This is VA, this is VB. If you draw the bend moment diagram, wherever maximum sag, wherever maximum bend moment is there, at that point maximum sag also will happen. But you have allotted time is only 1 minute. We cannot afford to draw entire bend moment diagram and waste the time. This is how you have to manage. Take moments of all force about A is equal to 0, clockwise positive, anti-clockwise negative. So, minus VB into 100 plus 400 into 75 plus 200 into 50 plus 100 into 25 must be equal to 0. So, for this you do not require calculator also to find. So, VB you will get around 425. Now, VB value we found. Now, maximum bend moment. You have to calculate bend moment at E, D, C, and wherever maximum bend moment you will get, there maximum sag will happen. But bend moment at D means 425 into 25, then 425 into 50 minus 400 into 25 you have to calculate and waste the time. So, we also learned from strength of materials that wherever maximum bend moment is there, at that point shear force changes its sign. So where shear force changes its sign, at that point it has to be maximum bending moment. So we know how to calculate where shear force changes its sign. See here, here it is 425, stand here, look right side, 425, stand here, look right side, 425. Now cross the load. Will the shear force change its sign or not? Section right side downward is positive. Section right side upward is negative. Initially 425 was there. By the time you come here, it becomes 25. 425 minus 400 is 25 only. Minus 25. Here it is section right side upward, negative, minus 425. Come here, plus 400, minus 425. Minus 25 only. Shear force didn't change its sign. So here minus 25. Now cross this one. Minus 25 plus 200 plus 175. So shear force changes its sign at D. No calculation, nothing. Then maximum bending moment also occurs at D, which means that maximum sag also will occur under this point load, under 200 kilonewton. Like that we should answer. Okay. So we will write now. Now to find maximum bending moment we will not calculate. Bending moment is maximum where shear force changes its sign. As I explained, you have to travel minus 425, minus 25, here plus 175 at D. So, shear force changes its sign. Shear force changes its sign under 200 kilonewton load. Under 200 kilonewton load. So, maximum sagging bending moment. So, maximum bending moment occurs under 200 kilonewton load. So, maximum sag. So, maximum sag also occurs under 200 kilonewton load. So 200 is that. If at all you draw the bending moment diagram, it might have gone something like this way. Now if you take a cable, loading, this cable will take this position. Like this. This here is 100 kilonewton, 200, 400 kilonewton. This is maximum sag. See, we didn't calculate also maximum bending moment magnitude, but shear force changes the sign we have seen at D. Maximum bending moment, same location you will get maximum sag. How much is that they will not ask you, but where maximum sag occurs they will ask. Now, if you take, this is a cable, bending moment is 0 everywhere. This segments, all of segments only are under tension. If at all you build any structure made up of steel or concrete which takes this shape for this loading, then in the structure also no shear force, no bending moment, only axial forces will develop in the segments. Okay. That means if you build any structure which takes the shape of BMD, then that structure is subjected to only axial forces. wherever you take it. If you build the structure below the reference line, each segment is under tension. If you construct the structure above the reference line like this with both ends hinged, see, necessarily they must be both ends hinged because bending moment should be 0. At hinges only bending moment will be 0. So, both ends hinged support you have to build, and it should take the shape of the bending moment diagram subjected to same loads. Then bending moment in the actual structure will be 0. So, if you build a structure in this shape, that is called a theoretical arch or linear arch. In a linear arch, if you build it, bending moment is 0 everywhere. So, that is first told by Professor Eddy, so it is named after him. But if you are not able to build like this, if there is some error in building like that, then the bending moment in the structure will be directly proportional to the difference in the ordinates, difference in the error. From the theoretical arch, your actual arch deviates, let us say, because you could not build correctly. The more the deviation from the theoretical arch, the more is the bending moment in the actual arch. Like that. That's what Professor Eddy says. Okay. So, now we will take the 7th point. So, next point is 7th point. If we build any structure which takes the shape of BMD, shape of BMD means funicular polygon, which takes the shape of the bending moment diagram or which takes the shape of the funicular polygon. Funicular polygon also takes the shape of BMD. Okay, funicular polygon. Then shear force. Then shear force and bending moment are 0 everywhere. Are 0 everywhere in the structure. Such structures are called theoretical arches or linear arches. They are subjected to axial forces only. Theoretical arches are subjected to axial forces only. That axial force can be compression or tension depending on whether it is below the reference or above reference line. Below reference line means tension will be there, above reference line means segments are under compression. Okay. Now, let us see the 8th point. Eighth point will take up this structure only. In the 8th point, we want to see what is the structure below the cable. Now see, earlier I have drawn up to here, this is 8th point. Now we want to know what is below this one. If you extend this anchor cables, no, this is the hanger cables. The hanger cables will go something like this. Okay. Here there is a beam. And here there is a support. There is a hinge here. There is another hinge. Now, the ABC is over. This point, let us say D, E. Then this is called two-hinged stiffened girder. Now, assume that this is some gap is there, this is the road. Vehicles come, enter here, travel and leave the bridge. This is a bridge deck, okay. Maybe 10 meters width is there. We enter into the bridge, we leave the bridge. If the span is more, due to the load on the bridge, this beam will bend, deflects also more. So, because span is more means deflections will be very less, unacceptable deflections will be there. So, to reduce the deflection in the beam, to reduce the bending moment in the beam, what we do is throughout the length of the beam we support hangers, we keep the hanger bars. These hanger bars are attached to a cable and that cable passes through the through pulleys and they are embedded here. Actually, there is a concrete block will be there. This fixed one means is a concrete block whose length can be 3 meters to 4 meters and this cable is embedded into this one, that male and female cone Fresnel system or some system, you will pull them, hold them so that it will not come out. Here also same thing. Okay. Now, if the loads come here, say, most of the load is taken by the hanger bars. Those hanger bars transfer the load to the cable, so that on the beam net load is less, because most of them hanger bars have taken, so that here deflection will be less, bending moment is less, everything will be less, small size of the beam is also sufficient. That is why it is called two hinged, means two hinges are there, stiffened. Stiffened girder means it is stiffened with the hanger bar so that its stiffness is more, deflections are less. Okay. Now, this is actual construction. In the example, the entire thing they have thrown it out, simply it is subjected to horizontal UDL. That load comes where? From the girders. Supposing that if the two-hinged girder is subjected to UDL, throughout the length uniformly distributed load came, let us say, then entire load is taken by the hanger bars only. Beam will not take any load. Then this will shear force bending moment will be 0 and entire thing will be taken by this one. That means this beam is fully laterally or fully supported. Such type of problems we have studied in strength of materials like this. What you have studied is this way. Supposing that you have a wooden log floating on water. This wooden log weight, you take it say 5 kilonewtons per meter, A, B. Its length let us say 6 meters. Then what is the bending moment in the wooden log? You have a wooden log, its self weight is 5 kilonewtons per meter, it is floating on water. Then strength of material sir might have told you what water will do. Water will exert a uniformly distributed upward reaction like this. This is your water reaction. How much? 5 kilonewtons per meter. Then what's the bending moment diagram? Simply a straight line. This is your bending moment diagram. Bending moment is 0 everywhere. Why? This point center C say, stand here, look right side. If this downward load will give you clockwise movement, upward water will give you anti-clockwise movement. So net bending moment is 0 at C. Not only C, everywhere bending moment is 0. Now take it, reverse it, keep it here. If this beam is subjected to UDL throughout its length like this, okay. Now hanger bars are acting in the opposite direction, UDL is acting downward. We assume that these hanger bars are kept sufficiently close so that entire beam is fully supported everywhere. When low UDL is there, upward hanger bars is like UDL, downward is also like UDL. So they balance each other, support simply keep quiet. So no bending moment everywhere. Stand here, look right side. If this load gives clockwise movement, hanger bars will give anti-clockwise movement. So net moment is 0 from that. But same thing you have studied, if the same bar or wooden log is floating on water, okay, if a man is standing here, say, whose weight is say 1200 Newton, center he is standing, let us assume. If a man stands at center of the log, then UDL, the water reaction will not be like a point load. Entire water will not go down and like a blade, it will not offer resistance. Even if you have applied point load also, water will exert uniformly distributed reaction like this. So heavy man, you take it 1200 Newton weight is there, he is standing here. Then water will exert upward UDL, how much? 1200 by 6 means 200 newtons per meter length, 6 meters 1200. So they balance. Now what is the bending moment diagram for this case? Like this, center maximum. This is what you have studied, positive bending moment. It is like two overhangs subjected to upward UDL. This is your bending moment diagram. What is the maximum bending moment at center? Stand here, look right side. 200 into stand at center and look right. So you will get 200 into 3 into 3 by 2. 900 Newton meter. So this value is 900 Newton meters. This you have studied. Same thing you attach it here. Instead of UDL, some vehicles are going like a point load, it is acting, let us say, some W. Downward load is point load, but upward is UDL. Equivalent uniformly distributed load you will calculate. Now it is the second case. When you stand somewhere here, there will be some unbalanced vertical reaction, and that produces shear force and bending moment. So when there is part UDL or a point load on the two hinged stiffened girders, then beam will bend, shear force bending moment will develop. But if it is subjected to uniformly distributed dead load or uniformly distributed live load throughout its length, only then bending moment shear force is 0. Beam will not be loaded, entire load is taken by the hanger bars, and those bars will transfer load to the cable. Okay. So once they ask that point as a 2 marks question, when a two hinged stiffened girder is subjected to uniformly distributed dead load, bending moment and shear force are 0 everywhere, that it becomes like this. So fully supported. Okay. Now let us see that conclusion. First point is, if a 3-hinged stiffened girder, a 3-hinged means, in this case supposing that you put one more hinge, it becomes 3-hinge. If hinge is not there, 2-hinged girder. 3-hinged girders are statically determinate, 2-hinged girders are statically indeterminate to 1 degree. As I told you earlier, 2-hinged simply supported beams are also indeterminate. That is why some tension developed in the girder or beam. So, if a 3-hinged or 2-hinged stiffened girder means it is stiffened with the hanger bars so that bending moment is less. Stiffness is more, means deflection is less. 3-hinged stiffened girder is subjected to UDL throughout its length. Entire load is taken by hanger bars only. Shear force and bending moment are 0. Bending moment are 0 everywhere in the girder. Everywhere in the girder. When it is subjected to partial live load, LL means live load, partial live load, then there will be shear force and bending moment in the girder. That is the first thing. If you get doubt why it is like this, you take what you have studied in strength of materials. A floating log with UDL, no bending moment. But if any part load is there, then bending moment will be there in the log. That water reaction, whatever water is doing here, the hanger bars are doing. Okay, that is a strange beam. Whatever your vehicular loads are there, here applied load, like that. That is the analogy. Second point, why we should provide the stiffeners? Stiffeners means hanger bars. The purpose of the stiffeners or hanger bars is to reduce the bending moment and deflection in the girder. The purpose of stiffeners or hanger bars is to reduce bending moment and deflection. So, reduce bending moment and deflection is one of the option. Bending moment and deflection in the girder. This is the purpose. Then static indeterminacy DS for 2-hinged stiffened girder is R minus S. R means number of unknown reactions. How many unknown reactions are there here in the 2-hinged girder? When you are dealing with the 2-hinged girder, you will not worry about the cable. If you see London Bridge or something like that, on the two sides there are two towers. High towers will be there. Between the towers only you travel. The height of the tower, there will run a cable. On the other side of the tower, one more cable will run. Between the cables only the deck will be there. So the tower here, actually there is a big tower from here to here, sometimes 10 meters, 15 meters towers will be there. One tower here, another tower, between them we will move. So this is one separate structure, this is separate structure. Two hinged girder means this one. Okay. So two hinged girder is statically indeterminate to 1 degree because there are two reactions here. This is VD, HD. Here VE, HE. So number of unknown reactions are 4. What are they means? VD, HD, VE, HE. Equations of equilibrium available. Number of equilibrium equations available are only 3. What are they? Sigma x0, sigma y0, sigma m0. So R minus S means 4 minus 3 is equal to 1 degree. In one paper they asked this one, two hinged stiffened girders are indeterminate to how many degrees? 1, 2, 3, 4 like that. Then one paper they asked what is the purpose of the hanger bars? Reduce bending moment and deflection, like that. Okay. Then another paper they asked this one, when it is subjected to UDL throughout its length, what is the shear force and bending moment in the girder? Girder will not be loaded when UDL is there throughout the length because entire load is taken by hanger bars only. Why take hanger bars only means you have studied in strength of materials. If a log is resting on water or if a girder is resting on the hanger bars, situation is same. Okay. Now, these are the points in this one. Now, with this one, now that the cable takes the parabola shape, now what we do is, whether you build it with concrete or steel, if it takes the shape of parabola, bending moment will be 0. If it is in the below reference line, now it is subjected to tension. If you reverse it and build one structure, then you will get two hinged arches or three hinged arches. If a two hinged arch hinges only, remember that edges must be hinges. If two hinged arch or three hinged arch, if it is subjected to UDL throughout its length, then that arch will become a linear arch or theoretical arch because the arch takes the shape of the bending moment diagram of an imaginary simply supported beam. So, such theoretical arches, generally it is difficult to build because when loads are moving, shape of beam shape of BMD also changes. So once your structure is built and that shape you cannot change it. So theoretical arches or linear arches are impossible to build because loads are moving, you cannot change the shape of the structure dynamically once built. But so what we do is, but if loads are moving, whatever bending moment or shear force develops, magnitude will be relatively less in the arches. So we take that structural advantage of the bending moment being less. So we build the arches from this concept. Okay. It is difficult. Next point is this one. Fourth point we'll write. It is impossible to build theoretical arches for moving loads. Because bending moment diagram continuously changes. For stationary loads, once load is fixed, bend moment is fixed, then in that shape if you build the structure, fine. But if the loads are moving, then bend moment also will change. Depending on the position of the load, bend moment also will change. Then means already you have built one structure corresponding to one particular position of the load. If the loads move, shape will not change, but bend moment changes. So naturally, the theoretical arch behavior will be gone because there will be shear force and bend moment in the structure. Okay, that's why theoretical arches for moving loads you cannot build because bend moments will change. So now, but still we use the arches, but not theoretical arches we can build. Some other arches, 3-hinged arches and 2-hinged arches, where the shear force and bend moment will be relatively less. So for larger spans also, for bridge structures, we build the 2-hinged arches or 3-hinged arches. How to build, what are the concepts or issues involved in the 3-hinged arches analysis part of it, we will see.